Welcome to note set number 27, where we start getting into the topic of design of digital filters. We'll be talking about FIR filters and IIR filters in that order. And we'll start off with just some general issues and then get into, in the next set of notes, specific design approaches, starting with FIR. So the stuff in this note set is in sections 10.1 and 10.2.1 of Proaicus and Monolacus. So just revisiting this diagram, which we have seen before, and just pointing out why we can't really have an ideal filter. So, you know, discrete time gives us a lot of advantages for designing filters that are unachievable by analog methods, but they still can't work miracles. So the ideal filter is something that we hold up as, well, as an ideal, something that we would love to try to actually achieve, and we define it well, going back to our first encounter with this, we said we would like to define a filter such that if the input signal's Fourier transform lies completely inside the passband, the thing that comes out should be nothing more than an amplitude scaled version, perhaps, and a time delayed version, perhaps. So those two requirements led to speccing within the passband, so from minus B to B. So we'll say that suppose the input signal's Fourier transform lies completely between minus B to B. What we need is a constant magnitude, and we're speccing it here as a constant of 1. Doesn't have to be 1, but the important thing is that it's constant. And then the other thing is that we do allow a linear phase response, and we've always drawn it like that, and we'll get into a little bit more discussion as to what it means to have linear phase. But basically, linear phase is just as we're showing here. The phase function looks like a straight line that goes through the origin. So the slope of that line leads to the amount of delay that would be imposed upon a signal whose Fourier transform lies completely in this passband. Now we're showing this here for a low-pass filter, but obviously we could do similar definitions for high-pass, band-pass, band-stop, and other kinds of specialized filters. But we can just use this low-pass as our motivating example. Okay, going to the next slide here, we now ask the question, and we've asked this before, why can't we actually achieve an ideal filter in practice? And we've touched on this before, and we'll get into a little bit more detail on this. Interesting theoretical result on the next couple slides. So let's look at this ideal low-pass filter that we saw on the previous page. We can use this rectangular function, little p sub 2b. So since we're talking about a continuum variable here, 2b specifies the width of this. And we're defining so 2b is the width of the rectangle, so it goes from minus b to plus b. And then we have this phase term, e to the minus j omega nd, and we see the minus omega nd defines that linear function of omega. If we take the j out of there, leave the negative, we see that we have a negative slope of nd. And we're defining it this way over minus pi to pi, and then saying that it repeats everywhere else. So this is just a mathematical characterization of the diagram that we saw on the previous page. Now, just to explore what this thing looks like and to see definitively why we can't really have such a filter in practice, let's look at what happens when we put a delta function in. So in other words, we're trying to find the impulse response of this filter. So we let x be the delta function according to our DTFT theorem or theory that says that delta function transforms into a function that's equal to 1 at all frequencies. And so now for that input, our output will be the product of x times h. Well, this is just 1, so really we don't even need that. It's just going to be the h function. So we take our h function and put it down here. And now we want to find out what does this output look like. And so we recognize that if we can find the inverse DTFT of this, we can use the linear phase, or we can use the delay property of the DTFT to see that this linear phase response of the filter basically just imparts a delay on whatever the time domain version of that is. So we go to our table and we see that this thing actually transforms back to a sinc function. So this summation and this plus 2 pi k just makes this one rectangle repeat so that we get the periodic nature. So that's just the way that it's often written on a table. So we could instead get rid of all of this, get rid of the plus 2 pi k, and then state this part here. So omega is a member of minus pi to pi, and then it repeats elsewhere. So what we've just shown is that this is the impulse response of this. Let me see if I can clear some of this stuff up because it's getting a little bit messy here. Let me try a quicker way. There we go. So what we see is that the impulse response of this ideal low-pass filter looks like that. And so if we draw a diagram of this, we see we put in a delta function that happens, and this should be n, that happens at n equal to 0. And what comes out is an impulse response that actually starts before, and this goes on for infinity to negative infinity. So it starts infinitely long before the input actually causes it to happen. And so how could a real-world system actually know that infinitely far in the future that a delta function is going to come into me and I should start wiggling like a sinc function infinitely long before that actually happens? So it cannot do that. This is a non-causal system, and we cannot build non-causal systems at all. Okay, so we have this issue. We cannot build causal filters that are ideal. So that raises the question. So if we can't get this perfect rectangular frequency response, what can we get? And so there's a famous theorem proved quite a while ago. Paley and Wiener were very famous, especially Wiener, famous mathematical electrical engineering professors, and they liked to apply very theoretical mathematical analyses to answer very fundamental electrical engineering results. So the Paley-Wiener theorem says the following: if h of n has finite energy, which is something that we usually require of our filters, and h of n is equal to 0 for all n less than 0, so this is just the causal restriction, then this must be true. And so what does this actually show us? It shows us that for the kinds of filters that we are restricted to in real world, this integral must be less than infinity. And so if we look at this, this is putting some constraints on what this thing can do, especially where and how it can go to 0. Because as soon as the argument of a logarithm goes to 0, the logarithm goes to infinity. And so basically this is saying that if this h of omega goes to 0 over even just a small, very tiny small interval of omega, that means that we'll be integrating infinity over some small non-infinitesimal interval, and the area underneath the curve will exceed infinity, and this will not be satisfied. So this puts some serious constraints on what kinds of filters we can actually have that are finite energy and, more importantly, causal. Conversely, excuse me, if the magnitude response is square integrable and satisfies this constraint, then there does exist some h of omega that can be built from that magnitude with some appropriate phase, and the result will be, in the time domain, a causal impulse response. Going to the next slide, we delve into this Paley-Wiener theorem just a little bit deeper, and we say, okay, so if this is the criteria that must be satisfied, what shapes can we have for a frequency response? Well, basically this puts a limit on, as I just said, we cannot allow this magnitude to be equal to 0 on any interval. So we can't have a perfect stop band. There's just absolutely no way to do that. And really the best that we can do for a stop band is we can allow the frequency response to go to 0 at only finitely many points. So we can't have it go down to 0 and stay 0 over an interval, but we can have it go down to a point and then boom, right back up. And we can only have it do that finitely many times. And we'll see later on when we see some of our actual designs, we'll see that happening over and over and over again for these designs. So basically, if we think about this from the point of view of our rational transfer function view, because this isn't really saying anything at all about the structure of the transfer function. It's saying the only thing it needs to be is square integrable and correspond to a causal filter. But we're interested in implementing filters that also have a rational transfer function. So that comes from our standard form difference equation, which gives rise to things that look like this for frequency response, things that look like this for our transfer function. So that's what we mean by rational transfer function. It's a ratio of two polynomials in Z inverse, or equivalently in Z. And that gives rise to our pole zero diagrams and our standard form difference equations and our block diagrams. And so our goal is to find, pick some desired frequency response that we're trying to achieve, and achieve it with this kind of structure, a rational transfer function system. Now, just a word in passing here. Let me get rid of some of this clutter here. Just a word in passing. Notice that we said that the Paley-Wiener theorem says that we can let the frequency response go to 0 only at finitely many points. Remember when we talked about zeros in our poles and zeros diagram, and we talked about how we envision the surface of the transfer function, the magnitude of the transfer function rising up above the z-plane, and the way I've described this, I can't remember if I've described it in these notes, but I think I have. We kind of describe it as a tent surface, and it gets staked down to the ground with zeros, but it's a funny surface. It's like the surface of a air hockey game table. So there's this air being blown up. So unless we tack the surface down to zero, it will not touch the air hockey table. So a rational transfer function will satisfy this. We'll have only finitely many zeros that we can achieve, and even all the zeros won't necessarily be on the unit circle. But so if we have however many of our zeros fall right on the unit circle, that will be how many points we've tacked it down at. So obviously we can keep adding more and more zeros on our unit circle to try to tack this down, but there will be finitely many points where it will be equal to zero. And in between, the air hockey table is pushing that surface up. Now, if we put zeros close together, the air hockey table can't make it float too high up, but it will push it up some. So we can get a better and better stop band only by putting lots and lots of zeros tacking down the surface in a very fine grid right around the unit circle wherever we want it to go to zero. And we'll see that as we look at our filter designs. So this is what we're trying to do. We have some desired frequency response that we would like to try to achieve, and we may specify that as a true ideal filter, or we may specify it less stringently as an ideal filter. But that's our desired frequency response, and we want to try to approximate that the best that we can using some sort of rational function for our transfer function. So that's our goal. And here's how we typically spec these. So the specs that we're trying to meet show how much we're willing to give up from the ideal filter case. So for a low pass filter, and I'm really only showing here from 0 out to pi, and because I'm speccing this for the magnitude response, this will be an even function, so you'll know what it looks like from minus pi to 0. And so what are we doing here? We're speccing a few things. Let me try to get rid of this here. We're speccing a few things here. We're saying, here's a cutoff frequency for my passband. So my passband lives from 0 out to there. And then we have a stop band that goes from omega sub s out to pi. Let me put the pi back there. And notice that we have a gap between where the passband ends and where the stop band starts. And that's what we call the transition band. And so we're not really speccing too much about the system response there. We're just saying that we want to go from passband type behavior to stop band behavior, and whatever it takes to get there is fine. So now in the passband up here, ideally we would want this to be perfectly constant at 1, and we're allowing it to go as high as 1 plus delta p and as low as 1 minus delta p. So delta p is kind of a plus and minus deviation from 1. Now notice that this is being specced here or shown here in terms of the frequency response in absolute values. So we're looking at a value of 1 here, so we really want to be speccing this in terms of dB. So our passband ripple, this value 1 plus delta p, we would convert into a decibel version. So we take 1 plus delta p take 20 log 10 of that, and that will be our passband ripple in dB. So it would be an up amount and a down amount by that decibel value. And then in the stop band, starting at this stop band edge, we draw a line at some level delta S, and here it's being shown in non-dB form. So we take delta S, which is going to be a number smaller than 1, since we start up here at 1, and our stop band is going to be some fraction of 1. So we take some number smaller than 1, take log 10 of that is going to be negative, take minus 20 times that, and it will be positive. So the stop band delta S gets converted into a positive dB value, and that's why we call it the stop band attenuation. It's not the value, the actual value of the stop band, it's how many dB down is it from the passband. And since the passband is 1 in non-dB, we think of it as 0 dB in the dB value. So if we end up with a stop band attenuation of 40 dB, we're looking at this level being at minus 40 dB. So we say plus 40 dB because it's how far down from the passband. That way we don't have to spec this as a value separate from where this is, because we could be speccing this as, you know, the passband level we might want to be, say, at 20 dB. Then we still spec a stop band attenuation as 40 dB. That's relative to that, so that would be down 40 dB. So the actual level in the stop band would be 20 dB. So this is how we would spec our low-pass filter, and how we would do that. Other types of filters would be similar. So here's a, well, yeah, I should have said something on the previous page. As we let delta P, on this one, as we let delta P and delta S, well, same thing here. Yeah, this is exactly the same as on the previous one. As we let delta P and delta S go to 0, these become more and more ideal-like, and as we let omega S go to omega P, this transition region becomes narrower, and the whole thing, as we spec it here, looks more and more like an ideal filter. So, you know, clearly, as we let these things happen, it's going to get harder and harder to achieve those goals, and we'll see the impact of that as we go through our designs. So in particular, the width of the transition band is a big thing. The narrower you make that transition band, even if you allow delta P and delta S to be fairly large, trying to make the transition band very, very narrow will cause some real big challenges in meeting those specs. In FIR filters, we'll see that the length of the filter has to increase significantly as the transition band is decreased. Likewise, for IIR filters, the filter order will have to increase significantly. So anyway, this is very similar to the previous one, just you know, things are reversed, and what we see here is a pass band from omega sub P up to pi, a stop band from 0 up to omega sub S, and then the transition band in between those. But the definitions in dB are exactly the same, so everything is very, very similar. Okay, next slide. Slide number 8, we see a spec for our bandpass filter. And so there we have 2 edges to define for the passband, since the passband happens in the middle. And we'll have 2 different transition bands and 2 different stop band specs. And, you know, as I show here, there's no reason why the 2 transition bands have to have the same width. You may not need them or want them to be that way. Likewise, the ripple in the 2 different stop bands may not be desired to be the same. So you could spec two different ripple levels. Obviously, we have one passband, so there's only one passband ripple. And I don't show the conversion of those things into dB here because it's exactly the same as before. And again, as these things happen, the filter becomes more and more ideal and more difficult to actually design and more complex to actually implement. Next slide. Here we have a band stop filter spec. And so here the stop band, there's just one of them. We still have two transition bands and two different pass bands, and we could have two different specifications for passband ripple, and the two different transition bands could be different widths. But other than that, everything else is very similar to what we saw for the previous ones. Okay, last slide for this set of notes is just some discussion here of some general issues that we'll be considering as we go into our design. And remember, our goal is we're given some sort of desired filter that we're trying to implement. We're trying to make that shape, but we need to do it with a rational transfer function so that we can implement this with block diagrams and things like that, and difference equations basically. And so what we're trying to do is we've got some specs, so we've got a desired and we've got the goal of approximating this with a rational function, and we've got some specs, things that are like band edges and ripple levels, and our goal is to try to achieve those specs with the least amount of complexity, so the fewest number of multiplies and additions. And we'll see that that basically gets captured. For an FIR filter, we want to make the length of the impulse response as small as possible while still meeting these specs. And for an IIR filter, we'd like to make the order of the filter as small as possible while still meeting these specs. And to some degree, this complexity, through its link to the length and the order of the filters, does get linked to the amount of delay through the filter. So we'll keep that in mind. And we'll have two options, FIR filters and IIR filters. And what we'll see is that there's some fundamental trade-offs. The IIR filters are nice because we'll be able to achieve some really nice magnitude responses with some really low complexity implementation, but they will not be able to provide us with a nice linear phase response. Now, in some applications, linear phase response is absolutely crucial. So things like digital communications, radar systems, sonar systems, image processing systems, all of those have very crucial requirements for linear phase filters. And so there's been much emphasis on how to design linear phase filters, and basically those can be implemented with FIR filters, but not with IIR filters. And then from the perspective of implementing this thing, we've got recursive versus non-recursive implementations, and we've already talked about how there is a connection of that idea to FIR versus IIR, and also its impact on complexity. And then finally, if we're designing a filter, when we're all done with the design and we go to implement this thing, we need to make sure that the thing that we implement will actually be a stable system. Otherwise, as soon as we start putting an input into it, the output will more than likely grow without bound, and that would not be good. So what we'll find is that FIR filters, by their very nature, are inherently stable. So that makes the design process easy. You basically just say, I need the best FIR filter from a magnitude and phase point of view and a complexity point of view that I can get. And you just design it. So you can very easily set up some optimization process and let that optimization process go about its business almost automatically sometimes, and come up with a design, and it will be stable. On the other hand, IIR filters are not guaranteed to be stable. So if you just set up a design process and you go through it, you may get a so-called filter that looks like it achieves your goals, and then you find out that that design ends up being unstable and would not be a usable filter. So I believe that's everything. Yep, so that's the end of this set of notes, and I'll see you in the next set where we'll talk more about this idea of linear phase.